You ever look at a whole bunch of data and just have this gut feeling that there are patterns hiding in there? Well, today we're going to dive into clustering. It's a way for computers to find those hidden groups all on their own. Let's get right into it.
So, imagine you've got all this data. You've got measurements, you've got features, but the one thing you don't have? Labels. You have no idea what category anything belongs to. So, where do you even start trying to make sense of it all?
All right, let's make this a little more concrete. Let's say you're a botanist. You go out and collect data on some flowers, you count the number of leaves and the number of petals for each one. And that's literally all you have. You don't know the species. The question isn't, what are these called? It's more like, which of these flowers are like the others?
And this is where a really cool technique comes into play. It's called unsupervised clustering. And the name pretty much says it all. It's unsupervised for a reason. We're not giving the machine any answers up front. We're just going to let the data speak for itself and reveal its own natural groupings.
So what is clustering really? Well, at its heart, it's a kind of machine learning that takes a bunch of observations, like our flowers, and groups them together based on how similar they are. The absolute key here is that the machine isn't studying for a test where it already has the answer key. Nope, it has to figure out the groups all by itself, just based on the data you give it.
Now, there are a bunch of ways to pull this off, but one of the most common and honestly easiest to understand algorithms is called k-means. So let's just walk through exactly how it works step by step using our flowers. Okay, this might look like a lot of steps, but trust me, the idea behind it is actually super elegant and simple. It all starts with you deciding how many groups you want to look for. After that, the algorithm just repeats this simple two-step dance. First, it assigns points to the nearest center, and then it moves the center. It just does that over and over and over again until the groups settle down and stop changing.
All right, that's enough theory. Let's actually watch this thing work. So imagine we take our 9 flowers and we plot each one on a simple chart. We'll put the number of leaves on one axis and the number of petals on the other.
So right off the bat, we have to make a choice. This is the one big thing we, the humans, have to decide. How many clusters should it look for? Let's just say we've got a hunch there are 3 types of flowers here. So we're going to tell the algorithm k equals 3.
Now to get started, the algorithm needs a kind of placeholder for the center of each of our 3 clusters. And these points have a special name, centroids. You can think of them as the temporary shifting heart of each group.
And here's where the randomness begins. The algorithm just drops 3 centroids at completely random spots on our chart. Right now, they're just there. They don't mean anything yet, but that is about to change.
Okay, first step in the dance. Every single flower on that chart looks around and says, which centroid am I closest to? And then it joins that team. So we get these initial red, blue, and green groups.
Now that those initial teams are formed, it's the centroid's turn to move. Each one calculates the exact middle, the average spot of all the points in its group, and bam, it jumps right to that new location. But wait a second. Because the centroids moved, the whole landscape has shifted. See that flower there? A second ago, it was closest to the red centroid, but now it's actually closer to the blue one. So we have to do the whole assignment step all over again.
And you guessed it, if the teams get shuffled, the centers have to move again. The centroids once again find the new middle of their updated teams. But notice something here. The movement this time was a lot smaller. The whole system is starting to settle down. So this little back and forth, this reassigning points and moving the centers, it keeps going until eventually we reach a point where no flowers switch teams. The groups are stable. And just like that, without knowing anything about flowers, the algorithm has found 3 distinct clusters in our data. Pretty cool, right?
Okay, so the algorithm did its job. It gave us 3 groups. But hang on, how do we know if these groups are any good? I mean, how do you grade the algorithm's homework when you don't have the answer key yourself?
And that's a huge point about unsupervised learning. We're not checking for correctness. The goal is really to measure the quality of the clusters themselves. A good set of clusters is when the points in each group are huddled tightly together and there are big, clear gaps between the different groups.
And of course, we can measure this with math. There are a few key metrics, but they all basically boil down to answering 2 simple questions. 1, are the points in a cluster close to their own center? And 2, are they far away from the centers of the other clusters? There's even a popular score called silhouette that kind of rolls all of that up into one simple number to tell you how good the separation is.
All right, so after all of that, what is the big idea here? What should you really walk away with from all this? It's this. Clustering algorithms like the k-means we just saw are these amazing tools for finding the hidden, natural structure in your data when you don't have any labels. Whether it's grouping customers by what they buy or finding different types of galaxies in space, it lets us find patterns that we never would have seen otherwise.
But this leaves us with one last, really interesting thought to chew on. The algorithm is the one that finds the groups, but we were the ones who told it to look for 3 groups in the first place. So here's the question. Did we actually discover a pattern that was already there? Or did we kind of create it just by asking the question that we did? It's something to think about. Thanks for tuning in.